So this week's lecture covers sections 4.2, 4.3, and 4.4 in your textbook. And I'm going to start by talking about backtracking algorithms. So backtracking is one of the most systematic ways to solve a constraint satisfaction problem. Instead of generating every possible assignment at once, we build a solution step by step. We assign one variable at a time. As soon as a constraint can be evaluated, we evaluate it. If a partial assignment violates a constraint, we stop exploring that branch immediately and basically cut that branch off. And so by doing that, we do not continue down a path that we already know is impossible. And this makes backtracking an efficient algorithm. It avoids wasted exploration and focuses attention only on assignments that still have potential. So that's backtracking. And then I'm going to discuss backtracking specifically in cyber configuration. So backtracking shows up constantly in security configuration. When we assign roles, permissions, or network zones, we are assigning values to variables under constraints. Suppose we assign a role that violates separation of duty. That branch should be rejected immediately. Suppose we grant a permission that exceeds a user's clearance. That configuration should not proceed further. So strong security systems will prune insecure combinations early. They do not wait until deployment to discover the violations, but they prevent the violations from actually being deployed. So in this sense, backtracking models are proactive policy enforcement, like a type of proactive policy enforcement. And then we can also think of constraint satisfaction problems as graph search problems. So each node represents a partial assignment of variables. And then from that node, we choose an unassigned variable and try values that remain consistent with the constraints. The start node is the empty assignment, and a goal node is a complete assignment that satisfies every constraint. And this view connects CSPs directly to the search algorithms that we studied earlier. And the order in which we assign variables matters. Good ordering can dramatically reduce the size of the search space. So that's how you think of a constraint satisfaction problem as graph searching, or as a graph search problem. And then consistency algorithms try to reduce the search space before we begin deep exploration. So instead of waiting for a full assignment to fail, we remove impossible values early. A variable is domain consistent if every value in its domain could still participate in a valid solution. If a value already violates a constraint, it should be removed immediately. And so in that sense, this shifts reasoning from reactive to preventive. And we shrink the problem before solving it. And then that often makes the remaining search much easier. So the idea, basically in summary, is to prune the domains as much as possible before selecting values from them. And then we'll talk about a constraint network. A constraint network gives us a structured way to represent a constraint satisfaction problem, because each variable is a node. Each constraint connects the variables involved. Every variable has a domain of possible values, and this representation makes dependencies visible. Instead of thinking only in equations, we see how variables influence one another. When we later discuss arc consistency, this network structure becomes critical. Constraints propagate along the edges of this graph, and the shape of the graph affects how pruning spreads through the system. And then okay, just checking that the recording's still on. Okay, we're good. So next we'll talk about constraint networks in access control in order to apply this to the cybersecurity domain. So now we're going to translate constraint networks into the access control setting. Think of the variables as user, role, resource, and network zone. Each variable has a domain of possible values. The constraints represent security policy. Clearance must be greater than or equal to classification. So the person must hold an equal or greater security clearance to access a resource that has a certain security classification to it. Separation of duty must be preserved. That's another constraint. And network zones must align with resource sensitivity. And ARC consistency fits naturally here. It removes permission combinations that could never be valid. So instead of discovering violations later, we eliminate them early. The constraint network becomes a model of policy structure. And now talking about ARC consistency. ARC consistency focuses on connected variables, and ARC is consistent if every value in one variable's domain has at least one compatible value in the connected variables domain. If a value has no supporting partner, it must be removed. So this does not necessarily solve the CSP or the constraint satisfaction problem, but it reduces domains in a principled way. ARC consistency pushes constraint effects across the network. It is a structured form of pruning that often makes the remaining search much smaller. And then to continue with ARC consistency, the key idea in the ARC consistency algorithm is propagation. We consider arcs and make each arc consistent by removing unsupported values. The important question is whether an arc ever needs to be checked again. The answer is yes. If the domain of a neighboring variable is reduced, an arc that was previously consistent might become inconsistent. That is why ARC consistency algorithms revisit arcs when domains change. Constraints propagate through the network, and pruning in one place can trigger pruning somewhere else. And continuing with the ARC consistency algorithm, once all arcs are made ARC consistent, there are three possible outcomes. First, a domain might become empty, and if that happens, there is no solution. Second, every domain might shrink to a single value. If that happens, we have a unique solution. Third, some domains might still contain multiple values. In that case, the CSP may or may not have a solution. So ARC consistency has simplified the problem, but we still need a search procedure to finish the job. So now we'll talk about finding solutions with ARC consistency and domain splitting. So to solve a CSP completely, we often combine ARC consistency with domain splitting. First, we simplify using ARC consistency, like we talked about on the last slide. And if any domain is empty, we stop because no solution exists. And if all domains have one value, then we're done. But otherwise, we choose a variable with multiple values and split its domain into smaller parts. That's the domain splitting part of this algorithm. Then we solve each subproblem recursively. This combines pruning with controlled exploration. And by doing this, we reduce the search space first, and then we explore what remains. So then, to view ARC consistency as prevention in the cybersecurity sense, we would consider that in cybersecurity, ARC consistency reflects a prevention-first mindset. We remove invalid privilege assignments before we ever explore full configurations. That means insecure combinations are eliminated early. The configuration space becomes smaller and safer before we begin deeper reasoning. So this reduces the attack surface created by bad options that should never have existed. And so the order matters. Prevention comes first and exploration comes second. So strong defensive systems rely on pruning before searching. And then to continue with ARC consistency and domain splitting as search, domain splitting turns the CSP into an explicit search process. Each node in the search space represents a CSP whose domains have already been made ARC consistent. If at least one domain still contains multiple values, we select a variable and partition its domain. Each partition becomes a new branch of the search, and we apply ARC consistency again. The starting point is the original problem after initial pruning, and a goal state is one in which every domain contains exactly one value. This combines reduction with structured exploration. And now we'll talk about local search. So local search takes a different strategy from backtracking. Instead of building a solution incrementally, it begins with a complete assignment. That assignment may violate constraints. The algorithm then repeatedly selects a variable to change and assigns it a new value. So the aim is to improve the overall configuration until no constraints are violated. Rather than exploring a tree of partial assignments, local search moves through the space of complete assignments, but it trades structure for speed and flexibility. And then discussing local search for CSPs. In local search for CSPs, we measure progress using conflicts. A conflict is any constraint that is currently violated. The objective is to reduce the number of conflicts to 0. We can formalize this by defining a function that counts unsatisfied constraints. The algorithm then attempts to minimize that value. When the count reaches 0, we have a valid solution. This reframes constraint satisfaction as an optimization problem over complete assignments. And now, applying the local search concept to cybersecurity, we'll talk about local search and security hardening. So local search closely mirrors how security hardening happens in practice. We often begin with a working configuration that is not fully secure. We measure policy violations, misconfigurations, or exposure risk. Then we modify one rule at a time. Each adjustment aims to reduce overall risk. Over time, the configuration improves. This incremental refinement reflects the practical reality of security operations, where systems are tuned rather than rebuilt from scratch. Now, iterative best improvement is a structured form of local search. And in this algorithm, we begin with a random complete assignment. At each step, we identify the variable involved in the greatest number of conflicts. Then we assign that variable a new value that reduces the total number of conflicts as much as possible. This is called greedy descent because we always move in the direction of immediate improvement. The method is often fast and intuitive. However, it can get stuck in local optima where no single change improves the solution, even though a better solution exists elsewhere. And randomized algorithms introduce controlled unpredictability into the search process. Instead of always choosing the best looking move, we sometimes choose randomly among conflicting variables. For example, we might choose the best variable most of the time, but occasionally pick any conflicting variable at random. This randomness helps the algorithm escape local optima. By mixing greedy improvement with random exploration, we increase the likelihood of finding a global solution. In large search spaces, a probabilistic strategy then outperforms a purely deterministic one. And next, we'll talk about stochastic local search. So, stochastic local search combines several techniques. It may use greedy descent to improve solutions. It may perform random walks to explore new regions of the search space. It may apply random restarts to begin again from a different configuration. The goal is balance. So, too much greediness causes stagnation. Too much randomness causes chaos. Effective stochastic search blends structure with exploration. So this approach is especially useful when the search space is large and complex. Now, in local search, we measure the quality of an assignment using a heuristic function. Often that measure is simply the number of conflicts. But we can also weight conflicts differently. Some constraints may be more important than others. In scheduling, for example, certain conflicts are more disruptive. We can define a function h of a that estimates the difficulty or cost of the current assignment. When h of a equals 0, we have a solution. Otherwise, lower values indicate improvement. This allows us to treat constraint solving as optimization. And now to apply it to a cybersecurity application. In cybersecurity, not all violations are equal. A minor logging misconfiguration is very different from a privilege escalation path. An exposed administrative interface is more severe than a small compliance gap. By defining H of A as a risk score, we can weight different types of violations according to their impact. The objective is not merely to eliminate the largest number of violations. The objective is to minimize overall risk. And this reframes constraint satisfaction as risk optimization, which better reflects real security priorities. Now we'll discuss random restart. So random restart is a simple but powerful idea. Instead of continuing to struggle with a poor configuration, we abandon it and begin again with a new random assignment. Each run is independent. If the probability of finding a solution in one run is p, then multiple restarts increase the overall probability of success. This technique is especially useful when local search gets trapped in local optima. Rather than trying to force improvement, we reset the search and explore a different region of the space. In large and irregular search spaces, random restarts can dramatically improve reliability. However, greedy descent has limitations. It can get stuck in a local optimum where no single change improves the solution, even though a better solution exists elsewhere. It can stall on a plateau where many neighboring states have the same heuristic value. It can struggle on ridges where improvement requires coordinated change in multiple variables. It can also encounter saddle points where progress requires changing direction. These structural challenges explain why purely greedy strategies often need randomness or restart mechanisms to remain effective. So now a word about optimization. An optimization problem extends constraint satisfaction by introducing an objective function. Instead of asking only whether a solution satisfies all constraints, we ask which solution is best according to some criterion. Each complete assignment maps to a real number that represents cost or utility. The goal is to minimize or maximize that value. This shifts the problem from feasibility to preference. Many real-world systems are not satisfied with any valid configuration. They require the most efficient, safest, or least costly configuration available. And so a constraint optimization problem combines hard constraints and soft constraints, kind of like what we talked about last week and that you considered in your assignment, for example. So just to review that, hard constraints cannot be violated. Soft constraints assign costs to different configurations. The objective is to find a complete assignment that satisfies all hard constraints while minimizing the total cost from soft constraints. And we can solve such problems using systematic search, local search, or pruning techniques like arc consistency. However, we cannot guarantee that a solution is globally optimal without systematic exploration. Optimization adds another layer of complexity to constraint reasoning. So a constraint satisfaction problem, again, consists of variables, domains for each variable, and constraints that restrict combinations of variables, or combinations of values, rather. A total assignment assigns a value to every variable. A solution is a total assignment that satisfies all constraints. Throughout this lecture, we've explored systematic search, pruning, local search, and optimization as methods for solving these problems. And the central idea remains simple. We are searching for assignments that repeat or that respect structured limits. The sophistication lies in how efficiently and intelligently we perform that search. Now, just to talk about dual representations. Some CSPs can be represented in more than one way. In the example of a crossword puzzle, if you've seen crossword puzzles where you're filling in, the puzzle has vertical and horizontal overlapping blocks where you fill in different words. So in a crossword puzzle example, one representation would treat each word position as a variable and each word as a domain value. The constraints enforce matching letters at intersections. A dual representation instead treats each square as a variable and each letter as a domain value. The constraints then enforce that the letters together form valid words. So both representations describe the same problem, but they structure it differently. And the choice of representation can significantly affect how efficiently the problem is solved. So in this case of a crossword puzzle, in one representation, domains are considered the words, and in the other domains are considered the letters. And so that can significantly affect the efficiency of one method versus another. So now let's consider variable elimination. So variable elimination is a different strategy for solving CSPs. Instead of searching through assignments, we remove variables one at a time. When we eliminate a variable, we combine the constraints that involve it and pass the resulting constraint to its neighbors. This effectively summarizes the impact of that variable without assigning it a value directly. The process continues recursively until only one variable remains. Then we reconstruct the solution by working backwards. Variable elimination shifts the work from search to constraint combination. And then when only one variable remains, we examine its domain. If the domain is empty, the problem was inconsistent. If values remain, we proceed backward to reconstruct consistent assignments for the eliminated variables. And an important detail is elimination ordering. The order in which variables are removed determines the size of intermediate constraints. Poor ordering can cause intermediate constraints to grow very large, making the problem harder. Good ordering keeps intermediate structures manageable and improves efficiency. And so now we'll apply this idea to a cybersecurity example of policy simplification via elimination. So in cybersecurity, variable elimination resembles policy simplification. Removing obsolete accounts, collapsing redundant rules, or aggregating layered permissions are all forms of elimination. However, order matters. Eliminating a highly connected policy element too early can create complex composite rules that are harder to manage. Poor elimination order leads to rule explosion. Good ordering produces simpler, more maintainable policy structures. And so this mirrors the computational trade-offs that we see in formal elimination algorithms. And finally, on this last slide, you see an example network. And this example network illustrates how variables and constraints connect in a structured way. Each node, and in this example, we have nodes A, B, C, D, and E. Each node represents a variable with a domain of possible values. And you see the domain of possible values being 1, 2, 3, and 4 for each node in this example. The constraints link variables and restrict which combinations are allowed. So you can see some of those constraints on there, like A cannot be equal to B, A must be less than D, and so on. These are some of the constraints. Even without solving the problem completely, the network structure here reveals how dependencies propagate. Highly connected variables influence many others. Sparse regions of the network are easier to simplify. And the topology of the constraint graph strongly affects computational complexity and pruning behavior. And so this concludes this lecture on sections 4.2, 4.3, and 4.4. And then if you haven't done so already, I encourage you to go to the online textbook and read those sections as well, together with what I've explained here. Hopefully that will give you a good understanding of this topic.